Hi, my name is Sayed Wakazimir. I will present a transformer model for image restoration. Image restoration is the task of recovering original image from its degraded version. For example, recovering a sharp image from its blurred version, removing rain to obtain a rain-free image, or restoring a clean image from a noisy image. CNNs have become de facto for image restoration as they can learn generalizable image priors from large-scale datasets. The fundamental operation in CNNs is the convolution that provides local connectivity and translation equivariance. But it causes two main issues. First, the convolution operator has a limited receptive field, thus preventing it from modeling long-range pixel dependencies. But for effective image restoration, the long-range relationships among pixels are important. For example, if we want to denoise the region of this red patch, we can exploit the information from the other similar patches in the image. The second issue is that once the CNN model is trained, the convolution filters have static weights at inference time, and therefore cannot flexibly adapt to the input content. Both of these issues can be dealt with the self-attention mechanism that calculates response at given pixel by a weighted sum of all other positions. Self-attention is a core component in transformer models, but with a unique multi-head implementation. The major bottleneck in vanilla self-attention is that its complexity grows quadratically with the spatial resolution of the input. For example, for an input of 10 by 10 pixels, the attention map is of size 100 by 100 pixels. But it quickly becomes infeasible to apply self-attention on high-resolution images. Images with such large resolutions are very common in image restoration datasets. As a consequence, existing restoration approaches either apply self-attention on small windows around each pixels, or divide the input image into non-overlapping patches and compute self-attention on each patch independently. However, restricting the spatial extent of self-attention is contradictory to capturing the true non-local interactions, especially on high-resolution images. In this work, we propose multi-head transpose attention, in which the key ingredient is to apply self-attention across channels rather than the spatial dimension. That is to compute cross-covariance across channels to generate an attention map encoding the long-range context implicitly. We also introduce depth-wise convolutions to emphasize on the local context before computing non-local interactions. In conventional feed-forward network, we propose two modifications to improve representation learning. First, we introduce depth-wise convolutions to encode information from spatially neighboring pixel positions. It is useful for learning local image structure for effective restoration. Second, we introduce a gating mechanism that is formulated as the element-wise product of two parallel paths of linear transformation layers, one of which is activated with a nonlinearity. The gating mechanism performs controlled feature transformation, that is suppressing less informative features and allowing only the useful information to pass further. Here is our overall encoder-decoder transformer architecture. We perform experiments for various restoration tasks such as image deraining, denoising, and deblurring. For image deraining, evaluation is performed on 5 different datasets. When averaged across datasets, our approach obtains 1 dB PSNR gain over the recent best algorithm SPARE. Here are some visual comparisons where our method reproduces rain-free images while preserving the structural content. For single image motion deblurring, we perform testing on synthetic datasets as well as on real-world datasets. Again, the proposed method shows considerable improvements over the other deblurring approaches. Here we present visual results. The images produced by our algorithm are more sharper than those of the others. Next, we test performance of our restorer for the task of image denoising on Gaussian data as well as on real images. Our method performs consistently well on different datasets under different noise settings. Here are denoising examples. Our method restores clean images while better preserving image texture. Finally, we provide results for defocus deblurring on single image as well as on dual pixel data. Our algorithm achieves substantial gains. And these are a few defocus deblurring results produced by different approaches. We have released Code's pre-trained models and demos if you would like to try them. Thank you.